range signals are interrupted every 37 seconds for the transmission of station identification signals, which consist of 2 letters in International Morse code. For example, the Memphis range station broadcasts identification, which is TS. This signal is always transmitted in the N pair of quadrants first. If a pilot is flying some distance off a beam in the A zone, he will hear the A signal for 25 seconds, a pause, and then the station identification letters. But an airplane on the beam will hear the on-course signal for 25 seconds, a pause, and then PS from the N antenna, followed by PS from the A antenna. At most radio range stations, Z-type markers are installed. On a radio facility chart, the small triangle indicates the location of these markers. These markers are called visual cones of silence because they project a small unkeyed signal field vertically above the range station at the ultra-high radio frequency of 75 megacycles. These beacon signals may be received by an airplane passing overhead on a separate pre-tuned receiver, and as the airplane passes through this radio field, an amber panel light flashes. In this manner, the pilot has additional assurance that he is flying over a radio range station. The fan marker is another radio aid which assists the pilot in determining his exact location. Placed on beams at varying distances, such as 20 or 30 miles from range stations, it functions as a position marker. On radio facility charts, the exact mileage from each marker to the range station is indicated. Each chart produces a vertical, fan-shaped signal field extending across a beam and at right angles to it. The fan marker is keyed to signal its location by dashes. The marker located on the north or northeast beam gives off a 1-dash signal. The second, in a clockwise direction, emits 2 dashes, the third, 3 dashes, and the fourth, 4 dashes. These signals can be received visually on an aircraft receiving set and are transmitted on the same frequency of 75 megacycles as the station's location markers. The pilot can distinguish the fan markers from the station location markers, since the fan markers are not close to stations and they broadcast signals of 1 to 4 dashes depending upon location. For example, the pilot can see the 1-dash signal indicating that he is over the north beam marker at Cuba. The 2-dash signal shows he is over the east marker at Fisherville. The 3-dash signal flashes if he is over the south marker at Coldwater. Or the 4-dash signal if he is over the west marker at Hughes. Another radio fix or location marker is the intersection of radio beams. For example, a pilot flying from Waco to Fort Worth will start on the Waco beam at a frequency of 385 kilocycles. When he believes he is approaching the beam from Fort Worth, he will tune his range receiver to 365 kilocycles from time to time until he can pick up the on-course signals of that station. When he comes into the Fort Worth beam, a glance at his chart will inform him of his exact location. The pilot is further aided by his radio facility chart. It shows the range station symbol and indicates by shaded areas within the triangle two zones that are the A zones. In making an instrument flight on a beam, it is important to be quick in detecting the A or N signal, which indicates that the aircraft is sliding off. The pilot must be equally alert in making necessary corrections in flight direction in order to return immediately to the beam. On-course flying is not a difficult task, but requires the constant attention of the pilot. Assume that a pilot starts a flight from Fort Worth to Texarkana by instrument. He is aware that the beam is 69 degrees, directs his airplane at that angle, and attempts to hold to it. Very shortly, the pilot is aware that he is no longer on course because he hears the N signal with increasing volume. He realizes he is drifting to the right due to a brisk crosswind. To correct this, the pilot turns left to 30 degrees. This is a fairly large correction, but he realizes the importance of quick, effective action and the immediate return to the beam. It is apparent that this correction will be too great. The pilot intends to change direction to the right by splitting the difference between his original 69 degrees, which carried him to the right, and his corrected heading of 30 degrees, which results in approximately 50 degrees for his next course. The aircraft has now entered the A zone. The pilot knows he is now to the left of the beam and proceeds to turn right a few degrees. He decides upon 60 degrees, which splits the difference between the 69-degree course, which took him right, and the 50-degree course, which he is now following. He hears the A signal fading and knows he is approaching the beam. It is now apparent that he must make another correction, or else he will cross the beam to the right and slide off into the end zone. He continues his calculations by reasoning that a course of 50 degrees took him left of the beam, and his present course of 60 degrees will take him too far to the right. So he adjusts his course by splitting the difference, which is 55 degrees. His radio sounds the monotone, which tells him he is on the beam. Since his present course of 55 degrees is not quite correct, he decides upon a course of halfway between his present course, which is too far left, and 60 degrees, which was too much to the right. While on the beam at 57 degrees, he will split the difference between 55 degrees, which took him left, and 57 degrees, which is leading slightly to the right, and follow a course of 56 degrees, which holds him in the correct direction. The pilot has learned by a trial and error method the necessary correction for the wind on his left, which was an unknown factor, and is able to continue on the beam without difficulty. There are 5 common errors made frequently by inexperienced pilots in attempting to fly on a radio beam. First, when a pilot finds that he is flying off a beam and desires to make a correction, he may continue to turn. This will confuse him and may cause him to cross the beam at a right angle. He should remedy his condition by making a series of moderate correctional alterations of his course and hold each until he can definitely establish his location. Second, when a pilot is off course, he may attempt to make quick changes of direction while approaching the beam. but before actually entering the beam. Unfortunately, because of reflections from or absorptions by mountains, high buildings, ore deposits, bodies of water, and so forth, there frequently will be found short auxiliary multiple beams paralleling and giving off the on-course signal. He may confuse these with the true beam and be led farther off his course. A third common error is the failure to utilize the relative intensities of the A or N signal. This can be overcome by holding the volume of the airplane radio receiver very low. In approaching a beam, it must be remembered that the A or N signals are hardly audible above the monotone background. Volume control must be manual, as the automatic volume control position will make courses wide. The fourth error is in making violent corrections in approaching the radio range station, at which location the beam is very narrow. It must be recalled that the beam near a range station is only a very short distance from the middle of a bi-signal zone. Therefore, any violent correction may result in an almost immediate reversal from a broad A zone to a broad N zone signal, thereby causing the pilot quite unnecessarily to zigzag his course or to become confused regarding the location of the beam which he has been following. Finally, the fifth error the pilot may make is a failure to consider the element of drift. A pilot must keep in mind a picture of the beam and visualize the effect the wind will have upon the actual direction that his airplane will travel. In flying within a radio range system, a pilot frequently must determine his location in relation to the range station. This is known as quadrant identification or radio range orientation. One method of identification is the 90-degree method. The pilot, hearing an A signal, knows he is flying in either quadrant 2 or quadrant 4. He determines the average bisector of each A zone on his chart and then turns to a course which is at right angles to that bisector. As soon as he crosses a beam, he makes a 90-degree turn, always to the right. If he again hears the A signal, he knows he is back in quadrant 2. He orients himself, makes a reverse turn, and easily locates the beam, following it to the station. If, however, after turning, he continues to hear only the N signal, he knows he started in quadrant 4. Thus oriented, the pilot makes a reverse turn and has no difficulty in aligning himself on the beam. Among other methods employed in quadrant identification is the parallel method. The pilot flies parallel to the average quadrant bisector, noting the fading or increasing in volume of the zone signal. If the volume increases, he knows he is approaching the station. Then, if he desires to reach a station, he flies parallel to the east leg until the desired on-course signal is reached and over the north leg of the beam to the station. In peacetime, regular hourly weather reports are transmitted by range stations to aircraft over the same frequency as the A or N signals and without interrupting these signals. At each radio range station, a fifth tower has been constructed for voice broadcast and used primarily for weather reports. An airplane flying by instrument normally is equipped with a small filter unit on the receiver circuit and a three-way switch on the instrument panel through which the pilot can receive the range signals alone. or the weather report, or a combination of both the weather report and a background of A or N zone signal. Another important navigation aid is the radio compass, which exists in several forms. The simplest of these forms is a radio receiving unit with a left-right reading indicator on the instrument panel and a fixed antenna loop. This is used chiefly as a homing unit. The pilot tunes this set to the radio station to which he desires to go and turns his airplane until the needle is centered. With this alignment, as long as the airplane is headed directly toward the radio station for which it has been tuned, the indicator hand remains centered. Any headings of the airplane to the right or left of the station result in a corresponding opposite deflection of the hand on the dial. Another type of radio compass, more inclusive in its construction, makes use of a loop antenna which can be rotated inside its streamlined case. This has all of the properties of the radio compass previously described and serves in addition as a radio direction finder. With the rotating loop, the pilot may obtain bearings without changing the course of the airplane. In direction finding with this type of radio compass, the pilot or navigator merely tunes the receiver to a given radio station. This may be either an official radio range station or a commercial broadcasting station. The crank, which drives the loop and the bearing indicator, directionalizes the loop antenna toward the broadcasting station so as to center the hand on the radio compass dial. With the hand in this position, the pilot looks at the bearing indicator where he takes a directional reading. The indicator arrow now points directly to the radio station. By setting the outer dial scale of the bearing indicator to the corrected magnetic heading of the airplane and reading the tail end of the bearing indicator pointer, the pilot or navigator can determine a bearing on his chart from north through the radio station to the airplane. Two or more of these bearings can be plotted to determine the position of the airplane. If the pilot is flying a beam, he can determine his location by noting the intersection of the line from a radio station and the beam on which he is traveling. The automatic radio compass is the newest addition for homing purposes or direction finding. Its loop antenna rotates automatically. Operation of this compass is simple. It is switched on, the proper band selected, and the desired station tuned in. Exact tuning of each station is evidenced by a maximum deflection of the tuning meter. When a station is selected, the antenna and the bearing indicator needle automatically point to the direction of that station. Turning the airplane to that direction will zero the needle. Pilots have learned that the art of flying an airplane over a course, with or without visual reference to the ground, can be mastered easily and accurately if necessary dependence is placed in the various instruments at their disposal, and if they will take the time and patience to familiarize themselves with the many aids that radio facilities offer. Jeeps, trucks, tank transporters, half-tracks, busy on all fronts, and all are powered by the internal combustion engine. The principles involved in the operation of all internal combustion engines are basically the same. First of all, the engine is called the internal combustion engine because it develops power by burning a mixture of gasoline and air inside its cylinders. Let's look inside one of these cylinders. To see the parts and their functions more clearly, we'll use this simplified layout. It takes 4 strokes of the piston to complete one cycle of operation. Intake, compression, power, exhaust. Intake, compression, power, exhaust. The cylinder and its principal parts are the piston, the combustion chamber at the top, and 2 valves, the intake valve on the right and the exhaust valve on the left. The passageway on the right is the intake port, and the one on the left is the exhaust port. The air-fuel mixture enters the combustion chamber through the intake port, and the exhaust port permits burned gases to escape out of the engine. Now, to make it work, a charge of air-fuel mixture is needed in the cylinder. On the intake stroke, the intake valve opens. The piston moves down, creating a partial vacuum, and the mixture rushes in. When this stroke is completed, the intake valve closes, sealing the air-fuel mixture inside the cylinder. This charge will produce more power if it is compressed. So with both valves closed, the piston moves upward, ramming the fuel mixture into a smaller and smaller space. Now we're ready for the power stroke. The air-fuel mixture is ignited by an electric spark. The rapid expansion of the burning gases drives the piston to the bottom of the cylinder with great force. Our cylinder is now full of burned gases and must be cleared. So the exhaust valve opens, and the piston drives the gases out through the exhaust port. With the cylinder cleared, the exhaust valve closes. The cycle is finished, and the piston is in position for the intake stroke again. Remember, for each complete cycle, the piston moves 4 times. But notice that the valves move during only 2 strokes of the piston, intake and exhaust. Don't forget this. We'll need it later when we take up valve timing. Now all we need is some efficient way to harness the power developed by this up and down motion.
This piston is connected through a connecting rod to a crank. Just as in this setup, the leg is the connecting rod which transfers power through the pedal to the sprocket crank. In the same way, the up and down motion of the piston is converted into a rotary motion by its crank. This crank, or series of cranks, on a 4-cylinder engine, a 6, or an 8, makes up what is called a crankshaft. This crankshaft is really the backbone of the engine and must stand the thrust of every power stroke. The power is transmitted from the piston through the connecting rod to the crankshaft. Next, we add a flywheel. The power stroke of the piston now turns this heavy wheel, and it continues to spin. Just as one power stroke of the hand will keep this grindstone spinning. Now we have this spinning flywheel to assist the piston through the other 3 strokes of the cycle. In other words, first the piston drives the flywheel, then the flywheel drives the piston. All the power developed by the engine has now reached the flywheel, and through a series of mechanical devices, the power is transmitted to the road wheels. To fully understand the engine, we must know what makes the valve system function. Here is a complete valve in operation, but where do we get the power to run it? The crankshaft, when driven by the pistons and connecting rods, furnishes the power to operate the valves. So let's start with the crankshaft alone. It works in partnership with another shaft called the camshaft. In the engine, they function like this: the crankshaft driving the camshaft. On the camshaft are these cams, or lifts, one for each valve in the engine. Let's look at one from the end. This model will show the shape clearly. The pointed end of the cam is called the toe, and the rounded portion, the heel. Riding on the cam as it rotates is the cam follower, which in turn moves the push rod. On the top of the push rod is the rocker arm, which operates the valve. Here's the complete action. The toe of the cam pushes up on the cam follower. The push rod rocks the arm, and the valve opens. As the valve is opened, the spring is compressed. Then, when the cam no longer pushes up on the rod, the spring is free to expand, so it closes the valve. That's how the valves are opened and closed, but we still haven't learned what makes them open and close at the right time. We know that the timing gears of the shafts mesh together, with the crankshaft supplying the power to turn the camshaft. But the size of these gears is the big thing about valve timing. Right here is where we control 4 movements of the piston to only 2 movements of the valve. By making the crankshaft gear half the size of the camshaft gear, the crankshaft makes 1 complete turn to every half turn of the camshaft, or 2 to 1. So, with the cranks on the crankshaft rotating twice as fast as the cams on the camshaft, the piston will go through a cycle of 4 strokes while each valve operates once. And this gives us what we need: valves closed during compression and power. The manufacturer provides small markings on the timing gears to help you correctly time the sequence of valve operation to piston movement. The marked teeth we have indicated with white paint must be exactly matched. If these gears are assembled out of time, even as little as 1 or 2 teeth out, here's one of the things that can happen. The engine will start all right, but on the exhaust stroke, the exhaust valve will close too soon, and the intake valve will open too soon, letting the piston drive burning gas right into the intake manifold and on into the carburetor. Then we'll have a fire on our hands. This is only one example of what could happen, but it's proof enough that those valves must open and close at exactly the right moment. Remember, these gears must be properly meshed. There is another characteristic of engines called power overlap. Here on a 4-cylinder engine, there is no power overlap because each piston must complete its entire power stroke before the next piston delivers its power. But when we have more than 4 cylinders, the first piston is still delivering power when the next cylinder fires. So we have this overlap condition with 2 cylinders working together for part of the cycle. Any engine with more than 4 cylinders has power overlap. And the more cylinders, the more overlap. And as a result of more overlap, we get a smoother running engine. But remember, power overlap does not increase horsepower. It just brings about smoother engine performance. You have learned the basic principles behind the operation of the internal combustion engine. Remember them, because if you've got them down pat, you won't have any trouble from here on in.